Alright, so we see we need to prove Maschkes Theorem. Which is that we have a G module V with a submodule U then there exists a submodule W such that V is the direct sum of U and W. Of course, it's worth pointing out the assumptions are that the characteristic of the underlying field for the vector space does not divide the order of the group, and that we're dealing only with finite groups here. I should point out there's various reasons why we focus on the case of finite groups. For one, it's the most classical material that was studied first and is the most well understood, and because a lot of later work in representation theory has mostly been focused on generalizing. So there's other types of groups called Lie groups and locally compact groups. These are all examples of infinite groups that we don't discuss in this course, mainly because you have to have a background in differential geometry or topology to even introduce them properly. But there's a whole subject of representation theory in those subjects too, or another subject called Lie algebras, which is an entirely different branch of algebra. But there's lots of different flavors of representation theory, and most of them involve generalizing these theorems. Finally, there's also modular representation theory, which often focuses on what happens when the characteristic does in fact divide the order of the group. And if one wants to go study representation theory in graduate school for a PhD program, one actually has to study those other branches as well. But this is the foundation you have to start with. So this is the start we're going to focus on. Anyhow, let's look at this theorem. So I remember mentioning before, one of the ideas is that once you've got this submodule U, if you pick a basis for U, then you could get the corresponding matrices. You now have a matrix representation for your group. You take a basis for U and then you extend it to all of V. And so then you have a matrix representation for your group. And moreover, it's going to be some sort of upper triangular business. And what you really want to have happen is to get a new basis such that you end up with block diagonal matrices. So one thing I should point out is that the reason why if you know linear algebra really well, at first this seems like it should be easy to get from upper triangular to block diagonal normally. You can just do Gaussian elimination and just subtract multiples, and if you remember Gaussian elimination algorithms very well, you know that that actually corresponds to creating a certain matrix and conjugating by it. And so for one matrix to get from here to here is actually doable. The problem is that you need to do this for every single group element, and it has to be the same matrix for every single group element. So in other words, that you found one matrix, A, such that you pulled this off. And it's not obvious that you can always do that right now. That's the thing we need to prove. So it's not enough to just try to do Gaussian elimination. You'd have to be able to prove that the same Gaussian elimination steps actually work for every single matrix in your collection of matrices. And so that idea crashes and burns very quickly. So that turns out not to be the proof. So this turns out to be a bad idea. But I mean, we can look at how we can salvage the idea. So what's happening here is you've fixed a basis. Once you fix a basis, this means that you've managed to once you fix a basis for U and extend it to V, you've actually rewritten V as a direct sum already. Literally, W is the span of the other basis vectors. And so this allows you to define a projection map. So literally, if you have your basis as E1 through EK, those are the basis vectors for U. EK plus 1 to EN, that's the remaining basis vectors. Then pi EI is either EI when I is less than or equal to K, or it's 0 otherwise. So this is what they call a projection, because you're projecting onto a subspace. Of course, the problem here is that W is not G invariant, which means it's not necessarily a G module. Necessarily. It might be. You might have gotten lucky. But from it we have this this linear transformation from V to U. This projection map. And V and U are both G modules. So that brings up a natural question. If you've got a linear transformation between two G modules in general, can you construct G invariant linear transformation, which means one that actually preserves the group actions, so that you actually get a homomorphism between the two representations. And this idea is actually important, and it's used in this proof and in other proofs. So rather than just do the special case here, I'm talking about the more general concept. And it turns out there is such an idea. What you do is you define, this is called the averaging function. You define L to the G of V to be 1 over the order of the group times the summation over every group element, G times L of G inverse of V. Note that as a function, what you're doing is you're taking, for a fixed group element, G acts on V prime as a linear transformation, so does G inverse. So this is a linear transformation from V prime to itself. From V to itself. This is a transformation from V to V prime. This is a transformation from V prime to itself. So this composition is a linear transformation from V to V prime. If you add linear transformations, you get a linear transformation. So So this whole thing is a linear transformation. And when you multiply a linear transformation by a scalar, you still get a linear transformation. So this whole thing is in fact linear, because it's a linear combination of a composition of linear transformations. And it turns out it is in fact, it does preserve the group action as well, which is kind of cool. Note here, this is where you have to assume that the characteristic doesn't divide the order of the group, because we're dividing by the order of the group. So note that this is assuming that this element exists in your field. And that only happens if the characteristic of your field doesn't divide your group. So if you don't know what characteristics are, that doesn't matter. Just assume we're working over complex numbers, in which case you can divide by any non-zero number, and that's not an issue. But if you're more sophisticated, this means you can work over Z mod PZ and other finite fields as long as you're working over the right characteristics. So not every characteristic works. So let's check that this transformation is in fact G invariant. So let me take an element G prime in in my group. Let me act on the vector V. By definition, I have this summation. And now I see I got the definition wrong. It's actually G inverse on the outside and G on the inside. There's always a mistake somewhere. So please note that correction. It's usually, this is the step in the proof where you realize whether or not you got that correct. All right, so we see that we have this fact. And what do we want? We want to prove that this is equal to G prime dot LG of G prime dot V. Of V. That's what we want. So we want to be able to pull a factor of G prime out. And one way to do that is to just introduce G prime and its inverse together in the right spot, like that. Because then certainly you can pull one of those G primes out of the summation. And then by properties of inverses, G prime inverse times G inverse is equal to G times G prime, parentheses inverse, L of G times G prime dot V. So here's where the kicker comes in. I can move the G prime on the outside. If I do a substitution here and I set H equal to G dot G prime, and I have H inverse L H dot V. And then I'm summing basically over all H times G prime inverse in the group. But the point is, as you sum over every element in this still goes over every element of the group. So by change of variables, you're really just going over every element of the group exactly once and then doing this conjugate transformation. There's a bijection between these two sets. And so each term appears exactly once. And so in the end, you are actually looking at G prime times LG of V. The only thing that's different is that you've changed the order of terms in the summation. But changing the order of terms in a summation doesn't change the value of a sum. And so this is still the same calculation. So it's worth pointing out, nothing in this proof requires this dividing by the order of G. But we'll see for Maschkes theorem that you actually get more power by adding on this constant factor. And there's other proofs where you'll see that dividing by the order of G gives you a lot more power. It's sort of a normalizing thing, because then your definition involves some sort of thing where what you're doing is called averaging. So somehow if you treat this as 1, you're adding up 1 G times. And so the average is 1. So back to Maschkes theorem, the point then is this operation with this particular projection map from V onto U is linear and preserves the group action. And pi g of g dot v is equal to g applied to pi of g of v. Moreover, if you take an element in the vector space U, pi of u is equal to u by the definition of how projections work. And g dot u is always an element in the vector space, subspace u, because u is supposed to be a submodule. So that means if I look at pi of g dot u, that's a subset of u. When I project, I still get a vector in u. When I multiply by g inverse, I still get a vector in u. If I sum over all elements in the group G, I'm summing a bunch of vectors in U. The result is in U. Particular linear combination of vectors in U is in U. And so I get that this is an element in U. Hence pi g of a vector in U is in fact in U. In fact, more to the point, pi of g, pi of any element in U is that element. And inverses cancel with each other. So you're summing over the vector u g times. So you're getting g copies of itself. And so you're not just getting an element of u, you're getting u itself. But this part tells you that G invariant subspaces are sent to G invariant subspaces. But here you get something even stronger with our projection map. Namely that elements in the vector space U are sent identically to themselves. In particular, that means that our homomorphism pi to the G is actually surjective. So pi to the G from V to U is surjective, because literally every vector in U has a preimage, namely itself. And so we can let W prime be the kernel. And because this is surjective, it follows that V is the direct sum of U with W prime. Because this is G invariant and preserves the action of G, it should follow that W prime is a submodule, which is what we wanted to show. So let's actually check that. V is in the kernel, G is in the group, then pi of G dot V, by definition of group action, you can bring the G to the outside. Then because V is in the kernel, it gets sent to the 0 vector. And because G is a linear transformation, G of 0 is 0. So, congratulations, you found your G invariant submodule by doing this averaging calculation instead. So that gives you a proof of Maschkes theorem. It tells you that every submodule has a complementary submodule. And then maybe in a later talk, I'll talk about why dividing by the order of G is a useful operation in general. And so the natural corollary was that every G module is a direct sum of irreducible G modules. Remember, irreducible means it has no submodule. Proof, induction on the size or dimension. And so case 1, V is irreducible. You're done, nothing to prove. Clearly it's a direct sum with itself. It's a direct sum with only one term. Case 2 is not irreducible, which means it has a submodule, a non-trivial submodule, say U. Then as we just saw, V is isomorphic to the direct sum of U and some other submodule W. Each of these has smaller dimension than V, and so by induction, U is a direct sum of irreducible submodules, and W is a direct sum of irreducible submodules. And so voila, V is also a direct sum of irreducible submodules. So then this usually brings the question one asks when you're given. So the same thing is true for representations. Given a representation, phi, this means that there exists a basis for your vector space, so that phi of G is block diagonal. In particular, you can get it so that you get a bunch of submatrices on this diagonal. And the point is that each of these submatrices is an irreducible representation, which means there's no way to factor them further. As upper triangular matrices. So this leads the problem of classifying representations into the following. So given a group G, classify all the irreducible representations. And then given an arbitrary representation, you know that somehow you can rewrite it as this direct sum. Where I goes from 1 to k, where these there are k irreducible representations. And then the question is, what are the AIs? So in other words, given an arbitrary representation, how does it decompose as a direct sum of the irreducibles? And so, as we will move on, these will be two questions we try to solve.